We're going to talk a little bit about Pearson's chi-squared test of independence. Amongst other things, the chi-square test can be used to analyze the relationship between two variables, x and y, that are both categorical or factors. And they can have two levels or more than two levels. But one requirement is that the groups formed by x are independent. That is, if x is whether an individual is exposed or not, the exposed and the unexposed group must be independent of one another. Well, technically, Pearson's chi-squared test is referred to as a non-parametric test, although it relies on having a large sample size, and it also uses a theoretical probability distribution, the chi-squared distribution. So it's very similar to the other parametric methods we've seen, like the t-test, analysis of variance, and so on. So while it is technically classified as non-parametric, it has a lot more in common with the parametric or the large sample methods that we've discussed so far. So we're going to work our way through this example here. So here, this is data coming from a paper published in the New England Journal of Medicine in 2002, and it's looking at an X variable of whether or not a child was vaccinated for MMR, measles, mumps, and rubella, yes or no, and whether or not they were diagnosed with autism, yes or no. And so the question here we'd like to ask is there any relationship between X and Y? So stating it generically, we're going to start with a null hypothesis that X and Y are independent or unassociated, or that there is no relationship between getting vaccinated for MMR and being diagnosed with autism. And an alternative hypothesis that there is some dependency or some association or some relationship between the two. So the main kind of probabilities of interest we're going to look at here is we're really interested in comparing two probabilities here. The first one, I'm going to label P1 hat. Okay, hat meaning it's a sample estimate from our data. What's the probability of developing autism given that they were vaccinated? And we can see we're conditioning on this row here. Out of the 440,655 who were vaccinated, 621 were diagnosed with autism. And this comes out to be 0.00141 or 0.141%. And the other probability we're going to be interested in looking at, or other proportion, is the probability of being diagnosed with autism given that they were not vaccinated. Again, that's conditioning on this row here. Out of the 96,648 who were not vaccinated, 117 were diagnosed with autism. And this is going to come out to be 0.00121 or 0.121%. So in some sense, these are the two proportions or probabilities that we're going to want to compare. And we're going to do it using the chi-squared test, although it's worth noting that often you also encounter this difference in proportions approach, making a confidence interval for the difference in two proportions or testing a hypothesis about the difference in two proportions. So we can also express the null hypothesis as being that P1 is equal to P2, right? That at the population level, these two proportions are equal. Or we can also express it that the difference in the proportions is zero, that there is no difference. And again, a reminder, often we express things this way because that boils things down to having one estimate that we can look at. One estimate we're going to test a hypothesis about, one estimate we're going to build a confidence interval for. And so similarly, we can state the alternative that these two proportions at the population level are not equal, right? The probability of being diagnosed with autism is different for those who are vaccinated and those who are not. And as noted, we can also state this as the difference in the two proportions is not equal to zero. So we're going to proceed through using the chi-squared test, but just a note, you can run through these two proportion tests and they're nearly identical. So a reminder that in hypothesis testing, we're generally comparing what we observed in a sample to what we would have expected to observe if our null hypothesis was true. So remember, we start by assuming the null is true and then see if we can provide evidence against that. So let's label that here. This here is our observed table, okay, which in notation we're just going to use O to represent the observed values. So now what we'd like to work out is what would we expect this table to look like if the null hypothesis really were true, if there were absolutely no association between X and Y, okay, or vaccination and autism. So here we have what we're going to label the expected table. Okay. With notation, we're going to use a capital E to represent this. So here we'd like to work out what would we expect this table to look like if the null hypothesis really were true and there was no association between X and Y. You'll notice here we're going to keep the row totals and the column totals fixed. Okay. So the idea here is thinking if we still had 537,303 people in our study, 738 who were diagnosed with autism, 536, 565 who were not. If we still had 440, 655 who were vaccinated, 96, 648 who were not, how do we expect people to be arranged inside the table? How many would we expect to fall in each of these cells? So let's choose one of the cells to pick on, and I'm going to choose this cell up here, those who were vaccinated and those who also were diagnosed with autism. So what we'd like to work out is what's the probability of falling in this cell? Okay, we're going to start there. What's the probability of being vaccinated and being diagnosed with autism? And now, you may recall a rule of probability. The probability of A and B both occurring is the probability of A times the probability of B if A and B are independent. Right? And here in our null hypothesis, we're assuming vaccination and autism are independent. So we can express this as the probability of being vaccinated times the probability of developing autism. Now in our sample, right, the probability of being vaccinated, 440, 655 were vaccinated out of the 537, 303. So this is the probability of being vaccinated, and the probability of being diagnosed with autism, 738 out of the total were. So 738 out of the 537, 303. So this here tells us the probability of falling into that cell if X and Y, if vaccination and autism are independent. What we'd actually like to get at is what's the expected number of people in the cell. Now you may recall from earlier stuff you've learned that to find expected number, we're going to look at the total number of people in our study times the probability of falling in that cell, okay, or N times P. And so again, we can think of this here tells us what's the probability of an individual falling in that cell, and if we want to know how many we expect to fall in that cell, we're going to multiply it by the total number of people. Right? The total number of people times the probability of falling in that cell. So multiply it by the 537, 303. Now one thing you may notice is that here, one of these are going to cancel out. We're going to be left with 440, 655 times 738 over 537, 303. Numerically, that's going to come out to be 605.25. And worth noting here, the expected number of people falling into each of these cells, sometimes written as capital E, is the row total times the column total divided by the overall total. So if we want to know how many people do we expect to fall into this cell here, it's the row total times the column total divided by the overall total. And so often when you see this stuff presented in textbooks, they give you this formula for the expected cell count. What we want to do here is get some intuition as to why is this the formula for the expected cell count. So remember, we're not going to focus on plugging into formulas and calculating values. That's not an important skill for us to build, but it is important for us to understand the underlying concepts and calculations that are going into these when we use a piece of software to get ourselves to the end values. One other important thing to note now is bring ourselves back to this idea of degrees of freedom that we've touched on throughout these series of videos. So we can notice with this table, we've started with 4 cells, or we can think of it as having 4 pieces of information. how many people fall into each of these cells. But taking a look at this here, the expected table we've started to build, hopefully you can notice we actually only have 1 degree of freedom. Once this is taken on a value, right, this here, the value in this cell is going to have to be a fixed number in order to get back to that column total of 738. And so we have kind of 4 pieces of information. We actually only have 1 degree of freedom. And so let's go in and fill in the rest of the values for the expected table here. So we're going to notice this has to be 132.75, right, again, to get us back to that column total of 738. This here, 440, 049.75. Okay, and again, you can get to these values by either figuring out which value gets you back to that row total, or by plugging into this formula here. But again, as noted, we're generally going to do this stuff using software. It's going to get us right to the end. We just want to understand what calculations is a piece of software doing, so we're not using a kind of black box approach where we throw some data into a computer and it spits out some numbers. We want to know how did it get those for us. So this final value, 96,515.25. Now, I want to bring you back to a reminder, hypothesis testing, we generally want to compare what did we observe in a sample to what would we have expected to observe if the null is true in some way, right? When we did the one sample t-test, it compared our sample mean to the hypothesized value for the mean. When we did a difference in means test, we compared the sample difference in means. How far is that from what we'd expect if the null was true, right? 0 or no difference. So we want to get at something that gets us the same idea of comparing what we observed to what we'd expect to have seen if the null was true. In order to do that, we calculate what we call a test statistic. Right, so these test statistics generally in some way compare observed to expected. And here we're going to call it a chi-squared statistic. To get this, we're going to sum over all the cells in the table. How far is the observed from what would be expected squared divided by the expected? Okay, so let's go through and sub in some of these values, again, just to see how we get ourselves to this test statistic. Let's start with the first cell here. Our observed cell count was 621. And how far is that from the expected of 605.25? We square that, divided by the expected cell count of 605.25. We're going to do this over all the cells, so I'll just jump to the last one here. How far is the observed 96,531 from the expected count of 96,515.25 squared divided by the expected count of 96,515.25. And if you work all this out, it's going to come out to be 2.28. This test statistic follows some distribution. It follows a chi-squared distribution, similar to what we've seen earlier, right? The t-test, we assumed our test statistic followed a t distribution. ANOVA, it followed an f distribution. So here's another theoretical probability distribution. This test statistic is approximately chi-squared distributed. And if the null hypothesis is true, and it has degrees of freedom, the number of rows minus 1 times the number of columns minus 1. Okay, and again, we don't want to get stuck on formulas, calculating degrees of freedom, and so on, but I want to bring you back to what we talked about earlier. Right? 2 rows, 2 columns, 2 minus 1 times 2 minus 1 is 1, right? That 1 degree of freedom that we talked about a little bit earlier. Okay, and then like always, we convert our test statistics into p-values. And p-values, while the way of getting at the exact numeric value changes slightly depending on if we're doing chi-square test, analysis of variance, if we're doing parametric or non-parametric or bootstrapping type approach, the mechanics change a bit. The underlying concept is always the same. We're always trying to get at what's the probability of observing what we did in our data, or something even more extreme if our null is true. Right? What's the probability of seeing a table that looks like this if the null is true and we'd expect it should look something like this? Or what's the probability of getting a chi-squared statistic greater or equal to what we observed if the null hypothesis is true. This is going to come out to be 0.1309, or about 13.1%. With that, what are we going to do? Right, our p-value is bigger than an alpha of 5%. We're going to fail to reject our null hypothesis. Right, our conclusion is we do not have evidence to believe that there's an association between vaccination for MMR and development of autism. I also want to bring you back to a reminder about test statistics. Right? The larger they grow, okay, the larger they are in value, generally the more evidence we have against the null. Right? And you can think here, if what we observed and what we'd expect were very different, right, our test statistic is going to come out to be a fairly large number. If what we observed and what we'd expect to see under the null are pretty similar, that tells us the null hypothesis is likely true. Right? What we saw and what we'd expect to see aren't very different. I also want to bring you back to some things we've talked about through these series of videos. A reminder that for really big sample sizes, and we have one of those here, right, for really large sample sizes, small differences sometimes can show up as being statistically significant. Also, for really small sample sizes, sometimes there may be big differences that don't show up as statistically significant. So I really want to bring you back to this idea that p-values are a guide. Okay, they're a tool that we can use to help us make a decision. They're not a magic number, greater than 5%, less than 5%, that answers our question for us, is vaccination harmful or not? We'll get to talking about these in a moment and how we can compare those. But first, I just want to get to the idea of assumptions. Like all these large sample approaches, or even the non-parametric approaches, they all have some assumptions that are built into them. So in order to work through the chi-square test, we're going to make a few assumptions. The first is that groups are independent, meaning that those who are vaccinated and those who are not are independent or different people. We're also going to assume that observations are independent. So person 1, person 2, person 3, they're all independent of one another. Then in order to do this test, we need all cells, okay, or all cell counts, to be greater or equal to 1, meaning we need to have at least one person in each cell of the table. And we're going to have a large sample requirement, like all these large sample tests do. And this is all of the expected cell counts, right? All of these here, the expected cell counts, are greater or equal to 5. Again, 5 being a guideline, it's not a magic number. This is the large sample requirement that's necessary in order to do the chi-square test, or in order to assume our test statistic follows a chi-square distribution. If this here is not met, if we don't have a large sample size or a large number of expected cell counts in each cell, some things we can do are use a non-parametric approach, or use an exact test. This one's called Fisher's exact test. Or we can also try something like a bootstrap type approach. A few more just kind of technical details for us to mention. The first is that we can do this chi-square test if the table has more than 2 levels for X or Y. So if we had, vaccinated, no, a little bit, a lot, or some form like that, something that had more than 2 levels, we can still do the chi-square test. It doesn't need only 2 levels. Another note worth mentioning, there's this idea of continuity correction. Okay, it's called Yates continuity correction. I'll give a very quick kind of intuitive explanation of what that is. The idea is that here our counts are on a discrete level, right? We have 1 person, or 2, or 3, or 4 in each cell of the table. So on a discrete scale, the probability, say that X is greater than 10, right? Having more than 10 people in a particular cell is the same as saying X is greater or equal to 11. More than 10, 11 or more mean the same thing when things only take on integer or whole values. On a continuous scale, if we're looking at something that's on a continuous scale and it can take on a value of 10 or 10.1 or 10.2 or so on, these mean different things. These are not equal. So that's the idea of the continuity correction, is that we're going from something that's measured on a discrete scale, and we're going to work out a p-value or probability using a continuous distribution. And to correct for that, the kind of suggestion for this correction is to sort of split the difference and use x greater or equal to 10.5. Right, so take the two statements that are equivalent on a discrete scale, which are not equivalent on a continuous scale, and use the midpoint. Now, one thing that we're going to get into following this is that the chi-squared test says nothing about the direction or the strength of an association. So if, okay, and this is a really big if because it's actually not true, but if we were to conclude that we have evidence to believe that vaccination for MMR and autism are associated using the chi-squared test, it wouldn't actually tell us is vaccination making you more likely or less likely to be diagnosed with autism. It also wouldn't tell us how much more or how much less likely. So you can kind of think of it as more like a screening test. It just helps us decide, do we think we have evidence that there's an association, or is there not any evidence that there's an association? To look at measures of strength and direction of association, we can work with things like the risk difference or attributable risk, the risk ratio, or the odds ratio. Essentially, those involve comparing these two probabilities here and either taking their difference or their ratio. Okay, but we'll expand on those topics shortly. So we just worked through this example here, looking at if there's an association between vaccination for MMR and development of autism, and we found that there was no evidence to say there's an association. And I thought, having this platform, I think it's important for me to say something here. Recently, there's been this kind of wave of anti-vaxxers or people being anti-vaccination, and I thought it was important to say a few things here. Now, I'm not going to speculate on exactly what goes on inside people's brains or why they might be thinking this or going down this path, but I do want to make some statements about science versus non-science. And so someone who's in an anti-vaccination kind of camp, they tend to make really alarming statements like vaccination leads to autism, okay? Which sounds like a very strong statement. And then as a scientist, what we have to say is we don't have any evidence to believe that there's an association between vaccination and autism. Okay, which sounds like a weaker statement, right? We don't have any evidence, but we're not really sure about it. And the reason is that as scientists, we know it's extremely difficult, if not impossible, to prove a null. Okay? It's very difficult to prove something doesn't happen. We always have to make statements like this, that we don't have evidence to believe something's happening. It's very difficult for us to definitively make these statements. Okay, so I think that's part of the problem, is that these alarmists make these really bold sounding statements, and scientists make these statements that sound weaker, like, oh, we don't really know and we're not sure. And that's not really the case. Okay, the case is that we don't have any evidence to suggest that they're associated. But it's nearly impossible for us to say that they are not associated. Where all this started out of was someone named Andrew Wakefield. In 1998, he published a paper linking vaccination for MMR and autism. Later, it was discovered, a lot of things were discovered. There were some huge conflicts of interest with him. It was found that the data was falsified, meaning the data was changed to make it look like there was an association when there's not. The paper was retracted. Okay, so it was published in the New England Journal of Medicine. It was actually pulled out of publication. They said that this paper was falsified, it's wrong, the person manipulated the data, and they removed it. Andrew Wakefield also had his license removed, okay, meaning they're not letting him practice as a doctor anymore. But this kind of falsified paper did a lot of damage, and it still lives on, and it still gets cited as a paper to say that the two are related when it's completely falsified.
Thanks for watching our video. Subscribe to our channel. Share our videos. Stick around, guys, because we got lots more. Statistics is hard to say properly. And not sign up properly. Okay.